This weighted cart is in a state of equilibrium, acted upon by several forces which add to a net force of 0. There's the force of gravity, which acts on the cart in the downward direction. There's the force of static friction, acting up the inclined plane. And the normal force acts perpendicular to the plane. In addition, there's a restraining force exerted by this block of wood. Let's produce another state of equilibrium, this time replacing all these forces except one, with two forces exerted by strings parallel and perpendicular to the incline. The one force we cannot replace is the weight, the pull of gravity on the cart. The mass of the weighted cart is 1.4 kilograms. To produce equilibrium, we need two forces to exactly add as vectors to produce the force of the weight of 1.4 kilograms. Notice that the inclined plane has three sides in the ratio of 3 to 4 to 5. Since the force on the right is perpendicular to the side AB and the weight is perpendicular to the side AC, these two triangles are similar. Therefore, we want F1 plus F2 to be equal to minus the weight. From trigonometry, we know that the right force is just the weight times the cosine of 37 degrees, and the force on the left side is just weight times the sine of 37 degrees. If the weight of the cart is just 1.4 times the acceleration of gravity, then we find out what F1 and F2 must be in terms of the masses that must be placed on the right and masses placed on the left. Using the trigonometric functions sine and cosine, where sine of 37 is 0.6 and cosine is 0.8, and using the mass of the weighted cart as 1.4, we find that the mass on the right must be 1.12 kilograms and the one on the left 0.84. Now we have 0.82 kilograms on the left side and 1.12 kilograms on the right side. If we have produced a state of equilibrium, we will not need the incline nor the block. As you see, we have established equilibrium.